Now today, my plan, as I'm fond of saying, God willing and the creek don't rise, today my plan is to finish up on chapter 5. A sharp-eyed student in section 505 on Wednesday pointed out that I'm behind. Somehow I thought that I had all this time because I had all day today also to finish chapter 5, but no, we're supposed to start chapter 6. That's all right. I think we will mostly catch up today, and certainly if we don't today, we'll finish catching up on Monday. That being said, I don't mind having gone a little bit slowly through some of that. This is some tricky material. And perhaps our last thing to tackle on stereoisomers, all the more so, is just conceptually difficult, hard to wrap your mind around. So I'll try to lead us through that. Let me just write R and S over here. In order to save us some time, I've already written out for you the absolute configurations of the chiral carbons in these 3 stereoisomers. As I said, we have just one more thing to talk about. And then I'm hoping to talk about types of reactions. It's something you'll have talked about in Gen Chem. Basically, not putting aside the whole thing about redox reactions, right? And by the way, not all reactions are redox reactions. This is something we'll cover later. And we'll learn that it's possible for a reaction to be neither oxidate, it's possible for it to involve no redox. There's no oxidation and there's no reduction. That can happen too. But besides that, I think if we're fair about it, there's really 4 kinds of reactions. And I think you've heard about these in Gen Chem. You've got addition reactions, which are basically of the type A plus B yields AB. So you've got 2 or more pieces coming together to make one big one. That's an addition reaction. Then you've got elimination reactions, also called decomposition reactions, which are the exact opposite of that. You've got one big thing breaking up into 2 or more things, like AB goes to A plus B. That's an elimination reaction. You've also got substitution reactions, of which there are 2 sub-flavors of that, though one of them we really don't often see in organic chemistry. They're usually inorganic reactions. And that's your single displacement type of substitution reaction. Those are of the type AX plus B goes to A plus BX. So you've got something hopping off of one piece and hopping onto the other. And those are things like MgO plus Cl2 yields MgCl2 plus 1/2 O2. That's an example of that type. But again, they're largely inorganic like that. The other type of substitution reaction, which is the type we'll usually see, and can be either inorganic or organic, is the double displacement. And that in general looks like AX plus BY yields AY plus BX. You've got 2 groups switching places with each other. And you had those out the nose in Gen Chem. All of your simple acid-base reactions are double displacement reactions. You know, NaOH plus 2 NaOH plus H2SO4 gives what? 2 waters and Na2SO4, right? The protons and sodium ions switch places, so to speak. So that's a double displacement. But most of the substitution reactions we'll learn about in organic chemistry, both this term and next term, also are of that type. And then the last type of reaction, it's not that common, but it happens sometimes. We just call it a rearrangement reaction. It's just one isomer turning into another isomer. You know, it's turning into another constitutional isomer or stereoisomer. That's it. And every single reaction you'll ever have to know, I think, will fall into one of those categories. And the reason you'll need to know that, I'm sort of getting a little ahead of myself here, maybe that's okay. The reason you'll need to know that is because that will be part of what it means to know a reaction, is to understand what class of reactions it falls into. Anything you can do to help yourself classify things, give yourself boxes to put things in, I think can only help, right? They do this in, of course, biology as well, right? We classify organisms by kingdom, phylum, class, order, blah, 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 right? It's useful to be able to categorize things. So we'll start out with that in chapter 6, though I might have just, since I can't help myself, I might have just now said most of it, but we'll go over that anyway. And then we'll also touch on radical reactions, also called homolytic reactions. There's another way of categorizing reactions by heterolytic or homolytic. And everything we've really looked at so far has been a heterolytic process, ones that involve movement of electron pairs. And candidly, 97% of the reactions we're ever going to talk about, maybe even 98, are all going to be of this type, are all going to be heterolytic processes, the ones that involve full arrows and pushing of full arrows. But there are radical reactions also, and I think you've heard of radicals, free radicals. You know that they're baddies in terms of our health. They're getting into your DNA and messing it up, right? It's a problem. And so you need to have your antioxidants that help to some degree to scavenge radicals. This is basically your blueberries, your pomegranate juice, largely anything that's a bright, pretty color is probably going to be good for you in that department. So, but there are important processes that are radical reactions. In the cell, I believe, again, I'm no biochemist, but I believe you will find radical processes in the electron transport chain. So that's why it's important to know what a radical process is. Beyond that, industrially, if any of you are going into engineering or materials type fields, boy, how many polymers do we make using radical reactions, and have we made for 70, 80 years, if not more? So all of your polyethylene, your polystyrene, polypropylene, et cetera, all of those are made by radical reactions. And so it's important to know something about how those work. Now, the way we draw mechanisms, the way we push arrows with radicals is a little different, because radicals are defined as single electron species. They're species with an odd number of electrons. There's an unpaired electrons somewhere in the structure. So if you need a definition of radical, there it is. A radical is defined as a species that has an unpaired electron somewhere, obviously very reactive. And so because of that, the way we draw arrows in our bookkeeping for our mechanisms is a little bit different. And I'm hoping to get that far today, though we may need to say a little more about that on Monday. And so please register your attendance, if you would, on REEF. I do have a problem for us to look at if there's time. I originally had a couple of REEF questions for you guys for polling, but I took a look at them and I thought, well, they're both things from today's lecture, so might as well put that off until Monday. I don't want to slam you guys too hard, or at least not that hard. Okay, so let's get back to what we were talking about. We'll finish up on chapter 5. And again, I think there's some things that you'll need to read about on your own. I'm pretty clear in the class notes about what you're responsible for and what not. For example, section 11 of this chapter on prochirality, I think that's beyond the pale. That's appropriate if we were maybe in an organic chemistry 3 course, if we were, you know, in a class for chemistry majors that were getting into fine details like that, then maybe. But I do not think that's appropriate for just a first semester organic chemistry course. Good. I'm the best. Oh, thanks. I'm not, but thanks anyway. Okay. So anyway, there's other things that you can read about on your own. I've had some questions about can other atoms besides carbon be chiral? Answer is yes. I don't think we'll really run into them. One that I think will shock no one is what about silicon? And indeed, silicon's right below carbon, forms 4 bonds just like carbon. Unlike carbon, silicon can become hypervalent, right, because it's in the 3rd row or below of the periodic table. So you can have 10 electrons around silicon, whereas you absolutely can't around carbon. But other than that, they're quite similar in many ways. Silicon can form 4 bonds, and so one could imagine a chiral silicon atom. You'd deal with it exactly the same way. You'd figure out if it's R or S exactly the same as you would with a carbon. I just don't think we're ever going to run into any chiral silicon atoms, but certainly compounds with chiral silicon are known. I'm pretty sure compounds with chiral germanium are also known. Germanium's below silicon, between silicon and tin. So there's things like that that you can read about in your own. I'll also just let you know there's some information about separating enantiomers, also called resolving enantiomers. And I don't know that I really care if you can write beautiful essays on the topic or, you know, finely sketched out diagrams. But I will have you know, it's very important to be able to separate enantiomers because of some of the things we've discussed before, right? We talked about the problem with, I'm blanking out on that morning sickness drug that I told you about. Dang it, hate when I can't think of a word. Well, and it's not just that one. It's, wait a minute, dang it. Thought it would be in the class notes. No, of course not. No such luck. Now I have to look it up just because it's bothering me. Thalidomide, that's it. But it's a problem to be able to give the patient just one pure enantiomer. And the reason it's a problem is because whereas separating diastereomers is very easy, or at least comparatively easy, because they have different physical properties, different solubilities, so it's relatively easy to separate two diastereomers. Separating enantiomers is very, very difficult because they have identical physical properties except for their again, I can't think of a word, their specific rotations, right? They'll be equal in magnitude but opposite in sign. Other than that, they're identical. They have the same solubilities, same melting point, same boiling point. So as you can imagine, separating enantiomers is for that reason very difficult because we don't really have very many properties that we can separate them by. There are some tricks that you can use, and the book does go through that, but I will say that being able to separate enantiomers is big, big money business nowadays. And I also will say that if you come up with a quick and cheap way to separate two enantiomers, you will become stupidly rich, and I will not begrudge you 1 cent of all of that money. You will have well earned it. So you can read about these things on your own. That being said, let's get back to enantiomers versus diastereomers, because there's one other issue that we began to touch on at the end of class the last time. And it's this. Remember how we said that for a compound with n chiral carbons, the maximum number of stereoisomers is 2 to the power n. And so in compounds like this with 2 chiral carbons, the maximum number of stereoisomers is 4, 2 squared. And we had an example of that last time, that you had 2 pairs of enantiomers, and any two of those stereoisomers that are not enantiomers would then be diastereomers. And that's very, very common. In fact, of the 2 situations, I believe that's by far the more common situation. But sometimes you run into a situation where actually there's only 3 stereoisomers. And what I want to get through here is how you can know when that's going to happen, or at least how you can have a hint, you know, something to put up that red flag and say, watch out, we could be in one of those situations. And you especially need to look for that if you're looking at a structure of this type. What are we calling these? Pre-Fisher projections or something like that? This is a possibility when the top and bottom groups are the same. That's something to look for. It's not a promise that you'll get it if the top and bottom groups are the same. But that's what I always look at first. If I see that, I go, uh-oh, watch out. We might get a meso compound here. Now, if the other 2 non-hydrogen groups on the other 2 carbons are different, then you'll get a situation just like we had the other day. And you'll get a chance to practice that on OWL later. Then you'll have 4 different stereoisomers existing as 2 pairs of enantiomers. But here, we have a situation where these 2 non-hydrogen groups are the same, they're both OHs, and the 2 groups on the top and the bottom, so to speak, are both carboxylic acid functional groups. And this is just an example. You also often run into these with cyclic compounds. Someone sent me an OWL problem just today. I got it this morning in my email that had one of these so-called meso compounds. So that's what we need to learn how to deal with and how to recognize it. But that's the first thing. If you're given a structure that's written using this convention, so you also need, as I said, to watch carefully with cyclic compounds. Basically, the bottom line is you're looking for something that has a plane of symmetry. And that's only going to happen in acyclic compounds when these 2 groups at the top and bottom are the same. So that's certainly the case here. Now, to save us some time, I've already written in the absolute configurations on those carbons. So that would be worth your time to verify that those are correct. And it's a little tricky sometimes to do these, but I do promise you those are correct. I've double checked them. For instance, on this compound, on this stereoisomer, both of those wind up being left turns, but because the H's are in wedge bonds, they're R, not S. So we went over that the last time. But anyway, these first two stereoisomers, these are enantiomers, right? There's a plane of, there's a mirror plane right here, and they're mirror images of each other. So those two are going to be enantiomers for sure, just as always. Let's see. So RR and SS are enantiomers. And again, notice the rule we went over the other day. When you're looking at enantiomers, when you go from one enantiomer to the other, all of the R's change to S's, all of the S's change to R's, no exception. That will always happen when you're comparing two enantiomers. But we also have this RS compound. And it looks for a moment, at least, like we're going to get yet a fourth stereoisomer. Let's write that one out. By the way, a question I often get asked, it's a reasonable question. You'll notice how when the OH group is on the left of the bond like this, you'll notice how I write HO in order to show that it's the oxygen that's attached. Will I take off points if you write OH? Yes, I will, because that shows me you're not really thinking about molecules and bonds. So we have to be a little bit flexible with carbon, because carbon is 4 bonds. So to linearize a methyl group, H3C, CH3, you know, we're more flexible with that. But with oxygen, we can afford to be picky because there's only 2 bonds. So we can show unambiguously, no matter which direction it's pointed, that is the oxygen that's attached to that carbon. So that's a good habit to get into, is thinking about connectivity, not just thinking of OH as an O and an H. We need to be thinking of molecules. Good, so we have, as I said, what appears at first like we're going to get another stereoisomer. This one would be SR. But lo and behold, when we look carefully, what we find is that these two compounds are the same thing. And there's a couple of ways you can prove that to yourself. One way is that if you take this compound over here and just flip it end to end like this, you'll notice it turns into the other one. Or if that doesn't work for you, here's another way to think of it. Let's say that you're standing over here at the bottom of that compound. Well, simply run up to the other side and stand in the other side. And you'll notice what you're looking at is this compound. That's another way to think of the same thing. So you can look at it either way. So in fact, those two compounds, those two structures, I should say, are not enantiomers. They're the same thing. Here's another way you can prove that to yourself. There's a plane of symmetry running down the middle of the molecule, either way that you draw it. And whenever you see that, you're looking at a meso compound, MESO. And it's a bizarre creature, but you do run into it sometimes, and you will need to know about it. You will need to be able to identify meso compounds when you see them. But I've given you some clues that at least you can have the red flag in your head go up, so to speak, that you might be in a situation where you'll run into a meso compound. I always look for it when I see these two groups being the same, but it's pretty common also in cyclic compounds. I don't have a chance to show you every single possibility you'll need to know about when you might run into a meso compound, but there's ample practice on OWL. But in this case, there actually aren't 4 stereoisomers. There are only 3, because this one that looks at first like the enantiomer of RS is the same compound. So RS and SR are the same compound in this case. One way to think of a meso compound is a compound with multiple chiral carbons, and they are legit chiral. They fall into the definition of chiral carbons that we gave in class, right? Each of those carbon atoms is sp3 hybridized and is bonded to 4 different things. So that falls into the definition of chiral carbons. Both of those carbons are chiral, but the molecule as a whole is not. And the way you can know that that's possible is by focusing on the definitions. right? We've defined chiral carbons, like I said, as carbons that are sp3 hybridized and bonded to 4 different things. We've also defined chiral compounds as those with 1 or more chiral carbons that are not superimposable on their mirror image. This is its own mirror image. As, again, you can verify, if you put a mirror plane, you'll get the other way of drawing the same compound. So that's how you know that it's possible to have a compound that is multiple chiral carbons, but is itself not chiral. Compounds of that type we call meso compounds. So they're kind of a bizarre and surprising thing, but they do exist. So again, what you need to know is that it's possible to have this type of thing called a meso compound. I don't say that what I'm about to say here is an exhaustive description of what you need to know. I'm just trying to give it to you just so that you have something to hang on to. And you need to be able to recognize meso compounds, that these are compounds that have multiple chiral carbons, but because it's its own enantiomer, because if all you do is turn the compound around, you get the same thing back, rather than getting an enantiomer. As long as that's the case, then you're looking at a meso compound. So strange as it sounds, it's a compound that is its own enantiomer, that has multiple chiral carbons, but is itself as a whole not chiral. And again, the way you know that's possible is by focusing on those definitions. And you'll see that those definitions perfectly describe a compound of this type, right? It is 2 chiral carbons. They really are chiral. It's not a trick, nothing up my sleeve. My hands never left my wrists. But the molecule as a whole is not chiral due to this plane of symmetry. Or because if you draw out its mirror image like we did over here, we find, lo and behold, we've just drawn the same molecule, drawn from a different direction. So instead of having 4 distinct stereoisomers that are present as 2 pairs of enantiomers like last time, sometimes we find there's only 3 stereoisomers in cases of 2 chiral carbons. And instead of having 2 pairs of enantiomers, we have 1 pair of enantiomers and a meso compound. And of course, that meso compound is a diastereomer of either of those 2 enantiomers. And again, the way you know that is by the definitions. We defined enantiomers and diastereomers. And that relationship falls under the definition of diastereomers. Yes? What? I'm sorry? Well, remember, the question is, is there a contradiction with 2 to the n? Does that not apply? Answer is no. Remember, we said 2 to the n is the maximum possible number of stereoisomers, not the number, the maximum possible number. So the maximum is 4. Here we have only 3. So it's not a contradiction. No, good question, though. One last thing I will tell you about meso compounds that just follows directly from all the definitions we've given in this chapter. If you took a solution of any meso compound and put it in a polarimeter like we described and did the beam of plane polarized light and all that, its specific rotation would be 0. Just as if you'd taken, done a polarimetry experiment on a racemic mixture, or just as if you'd done a polarimetry experiment on any other achiral compound. So if you get a specific rotation of 0, it means either the compound just has no chiral carbons in it, that's a possibility, or you're looking at a racemic mixture, or it's a meso compound. All 3 of those are possible. I'll say that again. If you get a 0 specific rotation, it means you're just looking at a run-of-the-mill achiral compound, meaning there's no chiral carbons, or you're looking at a meso compound, which is also achiral, or you're looking at a racemic mixture. And again, this or the next class will wind up on YouTube, so you can watch me say that as many times as you like. So it's a bizarre thing. It kind of hurts to think about a little bit, but it is something that happens sometimes. There are meso compounds out there. And so I've tried to spell out for you what you need to know about them. It's okay if you don't entirely understand right now. You need to go and practice with this in the OWL assignments. So I think that will help once you do that. But other than that, I think that's mostly it for chapter 5. Like I said, the rest I think you can read about on your own, but I've tried to at least touch on the topics there. Any questions about meso compounds, diastereomers, anything along those lines? This time I'm not even going to believe that it's because I'm such a good teacher that no questions. Well, or maybe maybe the reason there's no questions is sort of like you sense this is a tricky topic and you know you're going to need to go and think about it. That's fine too. So if you have any questions, well, I'll be around for my new Saturday office hours tomorrow, noon to 2. So feel free to stop by. I'll be glad to go over that with you guys. No questions other than, can you repeat that? And the answer to that is probably not, because I don't remember what I said. Do you mean repeat about the 3 things that give you a specific rotation of 0? I'll write it down. You have a chiral compound with no chiral carbons, just like ethanol, it's not chiral. You've got a racemic mixture. That's going to have a specific rotation of 0. We already talked about that. And you've also got a meso compound, which is also a chiral, but there are chiral carbons in it. Now, I know it sounds crazy. How can you have an achiral compound with chiral carbons? And the answer is because it's its own mirror image, because there's a plane of symmetry running through it. That's how you know you can have such a thing. Good, so it's there on the screen now. And I'll do the same in my next class so that you wind up with that on YouTube. You can pause the screen and look at it. Good, any other questions then? Okay, well, in that case, let's move on to start chapter 6. We still got 20 minutes, that's pretty good. I think that will be enough to get us through types of reactions. And really that is what I see as being the main point of chapter 6, or at least one of the main points, is how can we classify organic reactions? And right, and I think I've already said most of that. And we'll learn a few different ways of classifying reactions. And again, the reason you need to know this is so that it will help you to learn what you need to know about reactions once we start learning more of them. We're getting very close to the point where we can get into the real meat and potatoes, so to speak, of organic chemistry and start learning about reactions. But in order to know what you'll need to know about reactions, you have to be able to categorize them. That helps you to understand what's going on. So I believe I said that there's one major classification of reactions, which is heterolytic and homolytic. And you see the hetero and homo in there. That means different and same, right? So heterolytic reactions involve movement of electron pairs. And that's all we've seen so far. And we've talked about how to push arrows with them to draw correct mechanisms. We learned that mainly in the context of acid-base reactions, which is not wasted time, by the way, because you can almost you can almost argue that, I mean, if not every single reaction step you'll have to learn about and every single reaction you'll have to know, if not all of them, then most of them are going to turn out to be acid-base reactions of some kind, either Bronsted-Lowry acid-base steps or Lewis acid-base steps. And so homolytic reactions are the other class. They involve movement of single electrons because you're dealing with radicals, with species that have unpaired electrons. So we need to learn how to draw mechanisms of that type too. So that's one way we can classify reactions. The other types of reactions I mentioned before, it's basically, and I'll write them down, don't worry. It's basically addition, elimination, substitution, and rearrangement. Those are the 4 kinds. So addition reactions are basically of the type A plus B goes to AB. And you saw some reactions of this type in Gen Chem. What about Mg plus 1/2 O2 gives MgO? That's an addition reaction. You have two pieces coming together to make one big one. But we run into those very often in organic chemistry too, and we're going to learn about addition reactions of alkenes in chapter 7 a little bit, and in chapter 8 quite a lot. So if you add HCl to ethylene, you will get, actually let me make that a color because that'll make it easier to see. Whoops. You get chloroethane. This is an addition reaction. You've got two molecules coming together to make one big one. So that's how you know it's an addition reaction. And so it's possible even to classify reactions you've never seen before. And that's what I'm expecting you to aim to be able to do. That even if you've never seen that particular reaction before, you can still figure out which of those 4 categories it falls into. And you'll get to practice that on the chapter 6 owls. I'm pretty convinced. The opposite of an addition reaction is red. The opposite of an addition reaction is known as an elimination reaction. And it's simply the reverse process to what we just said. It's of the type AB goes to A plus B, or ABC goes to A plus B plus C. It's reactions of that type. So let's see. I probably gave myself an example over here. Sure. What if you took ethanol there are certainly ways of doing this. But if you took ethanol and you did a dehydration, you eliminated water and went back to ethylene, and the other product would be water, H2O. And I mean, it's not as simple as that. It's not that the water just hops off happily. You know, there's things you need to do in order to make that reaction happen. But we'll learn how that type of reaction can be done eventually, probably starting round in about chapter 7 or 8. But you can see that this falls into that category. You have one molecule breaking up into 2 molecules. And I believe if you go back and look at that reaction, you'll find the equations balanced for mass. So that'd be an example of an elimination reaction. Substitution reactions, at least the ones we'll learn about, are usually of the double displacement type. They're usually like AX plus BY yields AY plus BX. And you had those coming out your ears in Gen Chem, right? Do you guys remember doing precipitation reactions? Oh, I know you love those. Students love those things, right? Sodium iodide plus silver 1 nitrate gives silver 1 iodide precipitate plus sodium nitrate, right? The metal ions just switch places with each other. That's a substitution or double displacement reaction. What might that look like in an organic sense? Well, what if we took something like an ester and you hydrolyzed the ester? We'll learn about this reaction in organic too, actually. So the ethoxy group of the ester and the OH group on water switch places. And of course, that's not the mechanism, right? The mechanism doesn't go by these 2 things coming up next to each other and going, it's a little more complicated than that. It's about 4 or 5 steps, and we'll learn about it next term. But even if you don't know the mechanism, even if you've never seen that before, I would expect that you could look at this and say, well, I see two pieces that are switching places. So that's a substitution reaction. So that's just one example. And finally, the last major class of reactions is the rearrangement. And those are basically just isomerizations. It's converting one isomer into another. That's the definition of isomerization, converting one isomer into another. And those are not extremely common, but you do run across them. Let me give you an example. Something like this happens in, I believe, glycolysis, though, like I said, I'm no biochemist. CH2, C double bond O, CH2, OH, that's a 2, and you get in the end CH2, CHOH, C double bond O, H, because it's an aldehyde. So yep, that's right. So those two compounds are different. The way I know that is because of where the C double bond O is. This is a ketone, this is an aldehyde, but they have the same formula. All we've done is isomerized or rearranged that thing. And there is a step, I'm simplifying what R is. R, I think, is actually a pyrophosphate group. Would resolution be a substitution or rearrangement, like resolution of isomers? I'm thinking that in a net sense, it's neither of the two. Because is that what you mean, resolution of enantiomers? It looks to me like oftentimes with those you do some kind of addition reaction and then an elimination that kind of cancel each other out. But overall, during the whole process, it's none of those really. In a net sense, you just wind up with your two enantiomers at the end. But if I had my back to the wall, I'd say it's an addition followed by an elimination. And you'll see it falls into these definitions, I think, if you take a look at that. But I like how you're thinking, because you're already trying to classify things that we've seen. Good. So that's pretty much it for the types of reactions. With that, I want to start to basically what most of the rest of this chapter is talking about is learning more about how to push arrows, how to draw mechanisms. And the next thing that we need to approach is how to draw homolytic processes. How it is that we can handle radical reactions, and how do we draw arrows for radical reactions. And the first thing to become aware of, actually I should not have erased those words, is that for a heterolytic process, we use these normal arrows, right? Where the electrons start where the arrow starts and ends where the electron pairs rather starts where the arrow starts and ends where the arrow ends. And one thing I think you'll notice as you start learning about, so even though you get a different isomer, it's not really, I don't think you get different isomers with resolution, right? Nothing actually changes. All you've done is separated the enantiomers. So you haven't actually changed it to a different isomer. That's my understanding of chiral resolution anyway. But yeah, I don't think that's rearrangement. I think all you do is separate the enantiomers. You don't change them. Good, but as I was saying, there was a question in chat, by the way. If you look carefully at pretty much any heterolytic process, what I think you'll see is these arrows kind of play leapfrog. They go head to tail like this. And that makes sense, because if you're going to put an electron pair over here, you better take away another electron pair, right? And so they tend, you know, whether you have 2 arrows or 3 or 8, they tend to kind of follow the leader in a heterolytic process. In a homolytic process, that's not how it works, because in a homolytic process, we're going to use these peculiar fishhook arrows to show movement of single electrons. So notice the difference in shape between those. And therefore, the rules are going to have to be somewhat different. than for heterolytic processes. Because you're only moving one electron at a time. But if you think for a moment, each bond is going to consist of 2 electrons. So in order to make a bond, we have to move 2 single electrons together. So for a typical homolytic process, it might look something like this. I'll just put an example over here. I'll just be very generic about this. Let's say we have this radical X. And let's say we also have, what have I done here? Let's say we also have a species that's not a radical, that's an even electron species. Well, what we're going to have to do is take one of those electrons out of the bond there. We're going to see this happening shortly. If not today, then surely on Monday. And that's going to add to the single electron in the radical X. And again, we've defined radicals as species with an odd number of electrons, with unpaired electrons. And so, unlike with heterolytic type full arrows, homolytic arrows tend to come together. You don't see that really with heterolytic arrows. If you ever have 2 full arrows crashing into each other, likely you've made a mistake. In fact, I would almost say surely you've made a mistake. But with homolytic processes, that's what you're going to have. Meanwhile, the second electron in that bond is going to go on to this atom B. So you will have a new bond between X and A, and we will also have a new radical B. Something like that is what homolytic processes typically look like. And we're going to start off learning those. I still have 5 minutes, so I can at least get us started. We're going to start learning about these things in the context of halogenation of alkanes. So halogenation of alkanes is one of the few reactions that alkanes will undergo. Alkanes are pretty inert. One reaction of alkanes you know already from Gen Chem, combustion. It's just rapid combination with oxygen, and in a complete combustion, you'll be forming CO2 and water. That's the definition of a complete combustion. Only CO2 and water are formed. And these are usually pretty easy to balance, right? If you take, I don't know, hexane, which is C6H14, you combine with water, oxygen, you'll get CO2s, you'll get H2Os. So let's see, we need 6 CO2s. We have 7 H2Os, right? Because 7 times 2 is 14. Now we can balance the oxygens. We have 12 and 7 more is 19. So unless I've lost it, 19 halves. Or if you want to multiply everything through by 2, you did these in Gen Chem. But if this is something you've never seen before, then please Google combustion of alkanes or something like that. Look up something like that in your Gen Chem book. But these are usually very straightforward to balance just by inspection. They don't usually require a lot of work. Your Gen Chem book may not have liked these fractional coefficients. I see no problem. I think that's being too picky. I think an occasional simple fraction like that is just fine. But if you want to, you could also write it 2 hexane plus 19 oxygens is 12 CO2s and 14 waters. I'm fine either way. So that's one type of reaction of alkanes, is combustion, rapid combination with oxygen. The other type of reaction of alkanes is halogenation. And this is going to turn out to be a substitution reaction. And I'll just give you the, let's write halogenation here. Let me also write combustion up here. Just so you recall that you can burn alkanes. We do it every time we get in the car. In the case of a halogenation reaction, we're going to treat the alkane with some elemental halogen. That's going to be either chlorine or bromine. Those are the two that work. And this is going to undergo a substitution reaction. What's going to happen is one of the halogen atoms is going to change places with one of the hydrogens on the alkane. And so what you wind up with is an alkyl halide of some type plus the hydrogen halide. Sometimes we don't even write that part. One thing you might notice if you haven't even noticed already is we organic chemists are kind of sloppy about balancing equations by mass, certainly sloppier than you needed to be in Gen Chem, let's say. And so sometimes you'll find these inorganic side products mentioned and sometimes not. You'll know what you need to put based on how the question's phrased, but oftentimes we just ignore these, inorganic side products because we care so much more about the organic compound. So that's what we're going to get into next. And I think I might need to leave the bulk of that for Monday, and that's fine. I should mention the halogen needs to be chlorine or bromine. Fluorine does not work because F2 is much too reactive. F2 is crazy reactive. I've seen videos where they shoot a beam like of fluorine gas at asbestos, which like doesn't react with anything except like your lungs, but you know, it's very inert. And the asbestos glows red hot. So fluorine is crazy. If you treat an alkane with fluorine, you won't get a controlled reaction. It'll just tear it apart, and you'll get all kinds of little pieces with fluorines on them. I2, iodine, is the opposite problem. It's not reactive enough. You don't get a reversible reaction. You add iodine to an alkane, they just look at each other, no reaction. This type of reaction also needs to be initiated. It can be initiated by heat or by light of an appropriate wavelength or by a radical catalyst. And you'll see examples of how that's written and what you need to put in the book. We'll also talk about that a little bit the next time. But an example of a halogenation reaction, just to keep things simple, is reacting methane with chlorine. And the products are chloromethane plus HCl. So straightforward enough. I'm running out of time, but I just wanted to bring up, things get a little more complicated pretty quickly. I don't think we'll fully address this issue in chapter 5. I think we'll have more to say in chapters 6 and 7. But methane's pretty easy because all 4 of those hydrogens are the same. What if they're not all the same? That's when you have the possibility of multiple products. We'll eventually get there. The only other thing I want to mention is in order, and we'll say catalyst for now, or you can also initiate it with heat or with light. The other thing I'd like for you to notice is that we have another problem in that the chloromethane can in turn react with chlorine and give you dichloromethane, which can in turn react with chlorine and give you chloroform, CHCl3, and so on. So in order to solve that problem, in order to make sure we only substitute one hydrogen with the halogen, you need to add a large excess of the alkane. And that's how this is typically done. So you solve the problem of getting multiple halogenated products by adding a large excess of the alkane. And I'll simply end by saying that we're going to learn that a typical radical reaction is 3 phases. We're going to call those initiation, formation of radicals, propagation, getting more radicals back, and termination, which is when radicals get destroyed. And we'll go over all of those. You will need to know the mechanisms of all of those, but we're going to go over that the next time. So fluorine lights glass and fire. Yes, good point. Good. So that's all we have time for today. Have a great day. We'll see you on, have a great weekend. We'll see you on Monday.